I will stand up. It means it's time for you to kind of wrap up, okay?
Thank you very much. Good morning, everybody. My name is Phil Bart. The title of my talk is Collapse of the Bindschadler Ice Stream at 11.5 by Marine Ice Cliff Instability. I want to acknowledge my co-authors whose names you see there. Amy Leventer's here at the conference. I also want to acknowledge support that we got from the National Science Foundation to support our work here. So what you see here on this map of Antarctica, highlighted in gray, is the current location of the Bindschadler ice stream. At the LGM, it extended all the way out to the continental shelf edge into an area that's called the Whales Deep Basin there in eastern Ross Sea. This is the Whales Deep Basin. It's bound by the Hayes and the House banks. And a study by Massola and Anderson back in '06 showed that they used that red line there, which is multi-beam and seismic data, plus the little gray boxes, which are core locations, to show that the ice had advanced all the way out to the shelf edge, and then it retreated in the post-LGM. It paused about 50 kilometers inland and built a big, giant grounding zone wedge. And that made that bathymetric saddle that you see crossing the outermost shelf. Since then, there's been a lot of data collected. We got a great data set there. It's multi-beam, a lot of seismic, a lot of core, a lot of radiochronology, a lot of diatom and 4M biostratigraphy. We've got a really good understanding of how the ice sheet retreated from that area. It's a great framework. So that data shows that the ice moved back. Work from Conway showed that it passed Roosevelt Island at 3.2 thousand years ago. I'm going to show you a summary of what we've learned from this area using a line right down the middle of the basin. And I want to draw your attention to the upper image. I'm not going to talk about the bottom part, but it's showing in cartoon view the ice sheet all the way out to the right. That's the LGM position. And then since that time, it's contracted back. Its retreat is recorded by grounding zone wedges 1, 2, 3, 4. After the fourth grounding zone wedge, the ice shelf that was fronting the Bindschadler broke up, and then the Calvin Cliff existed. And that built additional 3 wedges on through grounding zone wedge 7. And then the ice sheet retreated. In this model, as of 2017, 2018, we thought it was with an ice shelf. And we've since questioned that interpretation. So that's what I want to talk to you about that today. So we have these objectives. So did the Bindschadler retreat with an intact ice shelf, or was it with a Calvin Cliff? Irrespective of how it retreated, what was the rate of retreat, and for how long were those rapid retreats sustained? So that's significant because this is really a collapse. This is a collapse, a big 200-kilometer line, grounding line translation. And we can gain some perspective about the ongoing changes, grounding line retreat, ice shelf thinning, and things from this paleo perspective. What you see here is the same cross-section that I showed you in cartoon view with a Calvin Cliff perched right at that big bathymetric saddle. And it's showing the Calvin Cliff there. The green arrow shows the location where we have 3 cores. They all show the same stratigraphic signature. They bottom into a grounding zone wedge diamond that was deposited on the grounding wedge 7 4-set surface. And then it's capped by an open marine facies. There's a lot of forams that occur on that grounding zone wedge 4-set. Enough so to give us good chronology of when that sedimentation ended. The dates tell us it ended at around 11.5. And then the ice sheet retreated and you got the open marine sediment to accumulate. The retreat is not recorded by grounding zone wedges, even though there was ample flux from this ice stream, but instead there's just tiny little small grounding zone wedges that are backstepping on that 4-deepened surface south of the saddle. This is a multi-beam image from the south of the saddle, and you can see this northeast-southwest orientation of those little tiny ridges. Massola and Anderson identified them in '26. Our survey in 2015 showed that they're very extensive across the middle continental shelf, and that's recording the retreat. This is them in line drawing view. There's more than 50 of them in the area where we surveyed it, and like I said, they're very small. Another key feature is that they're cross-cut by these iceberg furrows, and that can only happen if icebergs are calving near the grounding line. That's in deep water, and this is strong evidence for an ice cliff existing during the retreat. This is how the ridges look on chirp data. They're very, very small. This is an extract from the multi-beam survey using ArcGIS. I've shaded in 3 of the ridges with the gray. This is where we think the ice must have been each time one of those little backstepping ridges formed. That's a really small volume. You can see the scale bars there. And if you know the flux, we have a flux for the Bindschadler in its unbuttressed form, you can guesstimate how long it takes to deposit that ridge. Using that flux estimate, that would only take a few months, less than a year to make that ridge. And then it backsteps, it makes a similarly small wedge, and it does again the same thing. It's a very short amount of time that's elapsing as it deposits these ridges and moves back. Even if you add in the sediment between those wedges, it's just a really short interval of time, 1.5 years on that particular cross-section. During that same amount of time, the grounding line moved back 2.5 kilometers. So we can take the distance plus the time that's elapsed, the minimum time, to get a maximum grounding line retreat rate. So in this case, for that little short transect, it looks about 1.6, quite a rapid rate for the maximum retreat. This is an isopack across the entire area where we can survey the thicknesses of those little ridges. The darker blue shows thicker, so you can see the really beautiful trend of the individual ridges in the area. This is 2 of the 6 cross-sections that we created to measure the volume. And here I'm showing you in that second column the volumes that we estimated from those cross-sections. If you take that flux that we have for the Bindschadler ice stream, you can convert the volume to time. Here's the elapsed time. It's not much. The grounding line moves across that measured distance on those cross-sections. You can take that distance divided by the elapsed time, and you come up with rates of retreat. So in here we estimate the retreat rates were very rapid, on average 700 meters per year for those cross-sections. This is an image from Halberstadt et al. 2016. They made a prediction based on the orientation of megascale glacial lineations across the area in eastern Ross Sea that there was a big embayment in the grounding line across the Whale Steep Basin. So that's their configuration. And it's based on the orientation of the megascale glacial lineations to the west and east in Glomar, Challenger, and Little America Basin. That's totally consistent with how we reconstruct the retreat here. So there's the 11.5 grounding line right at the bathymetric saddle where the Calvin Cliffs existed. And this is the opening of that embayment. Its eastern flank is recorded by those little ridges that I showed you on the multi-beam. Okay? So there it is. Ultimately, it moves all the way back and stops at Roosevelt Island. That's a really big distance. More than 200 kilometers. So if you take our little rate of 700 meters per year, that would take about 3 centuries for the collapse to occur. That's consistent with what the modelers predict. So here's the ridge field again. The little X's show places where we have core. So I want to show you some of the core data. So this is the stratal type, the diamig directly overlain by open marine facies, right? On the south side of the saddle, we see there's a little bit of a section between those two. And we think that section was deposited in a very small sub-ice shelf cavity. It's partly informed by the Bassis et al. Model. And it's intermediate between things you observed in the grounding zone wedge, foreset and subglacial sediment, and that which you observed in the open marine. So I'll talk about those with 2 cores. A second thing we see is that the open marine condition gets interrupted. And we don't think that's the cavity, but I'll talk about that in a minute. This is the first of 2 cores I'm going to show you. It's showing on the right the interpretation of subglacial in the base. All of the cores bottomed into that till. It's overlain by this thin unit that we think was deposited in a sub-ice shelf cavity, and then it's overlain by open marine. So one of the things, the post-glacial is highlighted by the 2 red lines there. After you get into the post-glacial section, there's a continued presence of lots of clasts, suggesting that we were very close to the grounding line when those units were being deposited. Okay? Another thing is that they're very low in diatom abundance. That's what's shown on the far left column there. But there's a lot of rework stuff. For example, Stella Marina and Paralia in about the 5th column over. High abundances of things everywhere. So close to the grounding line. There's also an uptick in sea ice and ice edge diatoms that occurs within that facies. So again, we think that intermediate unit was deposited close to the grounding line, but also close to the open marine environment. This is a snapshot from the Bassis et al. Animation where they show a Calvin Cliff retreat. Ice is flowing left to right. The little red triangle we added in, that's the little morainal ridges, okay? Ice advances to there, and eventually erosion of the ice cliff above sea level produces buoyancy forces that creates a little sub-ice shelf cavity. This is when we think that sub-ice shelf facies was formed, putting it directly over the subglacial till. The iceberg eventually breaks off, the grounding line moves back, and you have the onset of open marine conditions. We see that pattern at all of the other cores, and that's what you see here. It's exactly the same as which I showed you on the first core. But after the onset of open marine, there's a transition back and an interruption of the open marine condition. We don't think that's the calving front or the grounding line moving back across that area. That's inconsistent with the morphological evidence of continuous retreat. Instead, what we think happened is once the grounding line retreated from the saddle, it moved back. Eventually, it moved its eastern flank past the Houts Bank into the deeper water of Little America Basin, and then it shed a bunch of ice after that buttressing was lessened, and that produced potentially the interruption in the open marine. Once that either melted or moved north, the open marine resumed. So we think we have a pretty good understanding of how it retreated. This is clearly a case where the ice did a very big grounding line transition within a short amount of time. We think the retreat occurred by marine ice cliff instability, opening at 700 meters per year for over 300 years. Thanks for your attention.
Great. So I have time for one quick question. Who's taking it? Do I have to run there? Catherine, you're closer.
It's a pity that Rob is not here, because your 700 meters per year is very different from the 12 kilometers per year in the marine ice sheet instability.
12, wow, that's high, yeah.
So we'll ask Rob that question when he comes. The first time you see him, ask him that.
Okay.
Our next speaker is, thank you so much, our next speaker is Jim.